Good morning and welcome to this lecture of analog microelectronic circuits. So in today's class we will start with our unit 4, and unit 4 is about operational amplifiers. So far in the first 3 units, if you remember the first unit we started with MOSFET. We understood the operation, the fundamentals of MOSFET, the DC analysis. After that we looked at the AC analysis, and we looked at various amplifier configurations where we can use this. In a similar way, similar approach we have taken for unit 2, where the device was BJT, bipolar junction transistor, but the rest of the analysis, whatever we have done for MOSFET, the same thing we extended to BJT. After that, coming to third unit, we had high frequency analysis of both BJT and MOSFET amplifiers. Along with that, we also saw another topic where we learned about how to bias in an integrated circuit. So for biasing, we were talking about current mirrors, the various different types of current mirrors, its advantages and disadvantages, and all the things we have seen in third unit. Now we are going to start fourth unit, where we will deal with op-amps, operational amplifiers. I hope you have heard about operational amplifiers even in the first year course, where this op-amp is one of the crucial block in all analog systems even today, because whenever we talk about any analog system or any analog circuit, operational amplifier is an integral component in that. So an op-amp is widely used in a lot of discrete applications. Some of the applications you have seen in your lab, AMC lab, where you performed experiments based on op-amp by selecting 74 on IC, and you have configured it as inverting configuration, non-inverting configuration, then Schmitt trigger, comparators, and all the other configurations you have seen. So the whole idea of unit 4, this unit is to understand op-amp in block level. We will not go to the circuit level details, what will be the internal circuitry of op-amp. We will not see that. Rather, we will look more on a block level and see various applications of op-amp. And the core of an op-amp is something called as differential amplifier. We will learn about differential amplifier and the internal circuitry of op-amp in the next course in the next semester, which is analog integrated circuits design. The second unit of that course is all about the internal circuitry of an op-amp. Alright, so this semester it will be pretty easy to analyze it in block level, and to do that we have to have some prerequisites, so that we will be covering in the first few classes. I hope that is good enough to go with op-amp. Alright, so I just want to write here a few things. One is, as I was mentioning, op-amp is one of the crucial block in all analog systems. So in between, if you have any queries, if you have any questions, please use the chat box. I'll be seeing the questions coming in the chat box, and I'll be responding for that. Right. So and I hope you are familiar with the op-amp from the AMC lab. So the first op-amp IC, the first op-amp has come in the IC form, and in the IC form has come, and it was named as mu A709, and it has come in 1960, and it was based on silicon. It was a silicon chip. This was the first op-amp IC, right? So now when we talk about op-amp, what is so special about op-amp? Can you just respond in the chat box? What is so peculiar about op-amp that we are discussing about op-amp? Why op-amp is important, or why op-amp is widely used? What do you think? Yeah, it can be used for various applications. One IC in many operations, alright, high gain, Yes, high input impedance. Alright, those are the features of op-amp. So in short, or you would have heard that we will be using op-amp. The name op-amp also suggests that it can be used for all arithmetic and logical operational amplifier, right? So it can be used for almost all operations. Now how these operations are being performed using op-amp, we have to look circuit by circuit, but in general it can be used for all arithmetic and logical operations. Now, as the name suggests, it is also an amplifier. So we know that amplifiers are widely used in many applications, because amplifiers are widely used in electronic block. It is used in communication applications where I need to pick up signal and to amplify. It is used in instrumentation applications where related to all the physiological signals in the body, and it is also used in all the computation related things, right? So these are the three common areas where we use amplifiers. And in general, if you look at an amplifier, what it does is, or why do you use an amplifier? So amplifier is a block which provides some gain of A. Now if you are providing V in, what we are expecting at the output, V out is equal to A times V in. And one important thing here is V out is proportional to V in the sense you have an amplification factor which magnifies your input signal to a larger value for whatever the application it is. Yes. Yeah, I can see some of the responses in the chat. It can operate on all range of frequency. Yeah, op-amp cannot be used for practically op-amp cannot be used for all range of frequency. It is having a limitation, like frequency limitation is there. We'll discuss about that. Alright. Yeah, so in general, if I look at an amplifier or if I look at the limitations of an amplifier, yeah, let us start from there. We look at the limitations of an amplifier, and there we will introduce op-amp, where we are expecting a lot of features, right? So some of the limitations of normal regular amplifiers is, one is, as we know, in an amplification or in an amplifier, what we are expecting is the gain factor. The moderate gain is generally available, or the availability of gain is not that high in regular amplifiers. That is why that is one of the limitation of an amplifier. We'll say moderate gain. Another one is another limitation is low input impedance. We always look for high input impedance, but the input impedance will not be that high in regular amplifiers. So you can think about any discrete circuit, but it again depends, or it again varies with respect to the circuit what we use, right? If it is a MOSFET based common source amplifier, input impedance is pretty high, but not the case with all the configurations. Then the other thing is the bandwidth, limited bandwidth. That is one of the other limitation. And the last one is the noise, or we generally call it as thermal noise, or the circuit should be immune to the noise in the noise, both from the circuit as well as from the surroundings, right? So an amplifier circuit should be capable enough to process a signal without getting affected with the noise, or it should be able to process a signal where the signal will be amplified and the noise will be suppressed, or those things should not appear at the output of the amplifier. So these are, if you look at amplifier, these are some of the limitations what we generally observe in the case of discrete amplifiers, right? Now if I ask this question, why do we need a why low input impedance is a limitation, or what is the need in general? In general, what we look is for high input impedance, and we also look for low output impedance, generally for voltage amplifiers, for the various reasons what we have looked before. Alright, so presenting these limitations of the regular amplifiers, there I am introducing op-amp, where when the op-amp initially it was proposed, let me write it as an ideal op-amp. So the limitations stated are these, and when now we propose an op amp, no, we are not proposing it now, I'm just talking about the time when the op amp is introduced. uh, the claim on op amp, or the features on op amp, are covering all the limitations of the regular amplifier. So in that way, if I look at an ideal op amp, so so covering the limitation in the sense, if it is the one of the limitation of a regular amplifier is moderate gain, op amp is supposed to give very high gain. Or in fact, if you talk about the ideal response or the ideal characteristics of an op amp, the op amp is supposed to give you an infinite gain. Alright, so that is how we characterize, or that is how we list the features of an ideal op amp, which can cover the limitations of the regular amplifiers. So before looking at that, let me also draw the symbol of an op amp. This is familiar for you. So generally we mark with 2 input terminals and 1 output terminal. This is not necessarily all the time, because in the next semester you will also see that the op amp can be, even the output terminals can be 2. So the moment you see two terminals to an amplifier, we call this as differential. This input is called as differential input. We will talk about this little later, more about this little later. So if you have two terminals where input is provided, we call this as differential input. Now the output is only one line, so we call this as single-ended output. This is single-ended output. Now what is the difference? I'll talk about what is a differential signal and what is a single-ended signal soon. Now just to present the symbol of an op amp, so we'll have this as minus, this is plus, and let me just call this terminal as V1 and this as V2 and this as Vout. These are the two input terminals and one output terminal of the op amp. Now since we are expecting gain, we usually represent the gain of op amp as A, or even we mark this as AOL, where AOL represents the open loop gain. AOL is open loop gain, or we mark it as A also. This is AOL. Now we know that any circuit can operate only when it is powered. So the other two things what we usually show in this symbol is two power supply terminals. We mark this as plus VCC and this as minus VEE. This is how we generally see the symbol of an op amp. Right. Now one difference here is, generally we say that one input and one output, but here the input is not single-ended input, but the input is differential, and it is also denoted with a symbol. Here it is marked as minus and here it is marked as plus. Since this is marked as minus, this input we call it as inverting input. This is inverting input, and this is plus, we call this as non-inverting input. Now why this is inverting and non-inverting, that make more sense when we look at the circuit of this the amplifier, the op amp. So this is non-inverting input, and this Vout is the output terminal. Alright, yeah. Now let us quickly see what are the characteristics of an op amp. So what are the characteristics we are looking at an op amp. So after listing that, we will talk more about the differential signaling and other things. Alright, so if I list the characteristics of an op amp, so I am listing the characteristics of an ideal op amp. So can you tell me what is Vout in this case? How can you write Vout? Can I get a response in the chat? So you can see a symbol over there. Output is marked as Vout. Input is, there are two inputs, V1 and V2. And what is Vout? Yeah, generally we write Vout as gain times input, but now the input is not a single input, you have differential input. So I'll take the difference of those two and mark as output. So V out is equal to A into V2 minus V1, or you can write V1 minus V2. In that time we will put a minus sign. Alright, this is one. So if I look at this op amp, one of the characteristics of op amp is op amp produces an output which is the output is actually gain times multiplied by the differential input. Alright. Now the second thing is, if you look at the input terminals of the op amp, so these two are the input terminals, and op amp is not supposed to draw any current in these two input terminals. So what is the meaning of that? If I say that op amp is not supposed to draw any current at the input side, what is the meaning? What is the implication of that? Can I get your response in the chat? Yeah, input resistance, yes, correct, Smriti. Input resistance is infinite. So when I say the op amp is not supposed to draw any current, it means that the input impedance is infinity. So let me write that. Op amp is not supposed to draw any current at the input side, or I can say the input impedance of the op amp should be infinity. So you can see that so we haven't marked any input resistance between these two terminals, or it is left open, meaning that for an ideal op amp what we assume is the input impedance remains infinity. In a similar way, we also say that output of an op amp should act as an ideal voltage source. Output of an op amp should act as an ideal voltage source. Can you tell me what is the peculiarity of an ideal voltage source? What is the peculiarity of an ideal voltage source? Say if I am marking a voltage source, an ideal voltage source, when I mark the resistance will be 0. So I can say that the output impedance should be equal to 0. Alright. Yeah. So apart from this, we'll look at the various ideal features of op amp. These are the things what we need to understand about the op amp in the at least in the first time, right? So the output is equal to gain times V2 minus V1, and input terminals should not draw any current, which refers to input resistance is infinity. Output should act like a ideal voltage source. That means output impedance should be equal to 0, right? So moving on, let us also see here what do you understand by this differential signaling and single-ended signaling, right? So in general, say I have a voltage source and I am taking output from this voltage source. Say this voltage source value is Vs, and if I am measuring this voltage across this voltage source, how will I generally measure? I will measure from this point with respect to a reference point, and the reference point is in most of the cases we will consider the reference point as ground terminal, right? So if I am measuring a voltage with respect to ground, we call this as a single-ended signal. So what I have marked, what I have shown now is an ideal case, but in general we'll know that there will be some resistance. It should be, even though it should be ideally 0, there will be some resistance, right? So and if I measure the voltage from this point with respect to ground, we call this a single-ended signal. At the same time, now if we look at a differential signal, the difference is this. So I have a voltage source, and if I have another voltage source, now both I can measure with respect to ground, right? So this I can measure with respect to ground, this also I can measure with respect to ground. But now if I am measuring the voltage across these two terminals, say I am considering this as plus and minus, and if I am measuring between these two terminals, now we call this as a differential signal. So what is the meaning of a differential signal? We are not measuring any voltage with respect to ground, with respect to a common reference point. Instead of that, what we are doing is we are measuring between 2 points. 2 points. Now, strictly speaking, these 2 points should have opposite signal variation. So what is the meaning of that? Say if at this node, if the signal is swinging in this form, in the other node, the signal actually should swing on the other way. What will happen otherwise? If both node will have equal signal variation, then the difference will be always 0, and that is what we need, right? So our need is not to take a differential signal and to say that always the difference signal will be 0. Rather, whenever we measure between 2 points, we should make sure that the signal excursion should be equal but opposite, right? So when this signal progresses, this should actually start on the negative side. So the inherent advantage of a differential signal will be always when you measure it will be twice, right? Say for example, this amplitude is V and this is V but starts with minus V, the differential voltage will be always 2V. That is an inherent advantage of a differential signaling. Are you guys with me? Can I get some response in the chat? Are you guys with me? What I meant by differential signal and single-ended signal? Alright. I hope you understood that. So we'll talk more about this differential signaling when we start differential amplifiers, but that is not in this semester. Alright. Now, so why I am talking about differential signal here is because op-amps, or the moment we say that we use op-amp, what we are expecting from this op-amp is op-amp responds only to differential signals. Or how we are expecting an op-amp to act is, if there is a differential signal, it should respond to it and it should provide a large gain. If the signal is a common mode signal, so that is the other term what we use. The signal is common mode, then it should not respond to that. So that is how we always say that when we talk about gain in an op-amp, we always classify gain into two. It is not classification. We talk about two gains. One is differential gain, which is a gain of the op-amp to an input signal when the signal is appearing in a differential form. The other gain is called as common mode gain, which is a gain which is for signals which are common in nature, right? We'll talk more about this again. So op-amp should only respond to differential signals, and the common mode gain of an op-amp should be very low. That means, say I'll also write here that the differential gain what we are expecting, if I mark it as AD, this should be equal to infinity, and common mode gain should be equal to 0. Now you will have this question, why all of a sudden I am talking about another gain called as common mode gain and that should be equal to 0? Because if you remember, we were talking about amplifier which should respond, or which should be immune to noise, right? So when I say common mode signal, say for example, if you have an IC or if you have any circuit, the common disturbances such as noise, whether it could be from power supply or it could be from the other sides, all this noise will be affecting all the nodes in an IC in an equal way. Say for example, if there is a disturbance from the power supply line, that will affect every point in an IC in an equal way. Similarly, equal way in the sense it will affect all the nodes in an IC in a common way. And now, say for example, if you have an amplifier and it is having the input terminals here, now the common mode disturbances will be affecting this node and this node will in a similar way, in an equal way. If that is the case, if the op-amp is not responding to this common mode signal, the noise will not come at the output. Are you getting the point? The op-amp is not responding to the common mode disturbances, then that disturbance will not be passed to the output. That is exactly what we need. So when I say the common mode gain should be equal to 0, the common mode disturbances will come, but the op-amp should not respond to that, or it should give a common mode gain of 0 or as low as possible, so that the effect of this noise will not be propagated further, right? I hope to some level you understood. We'll discuss more about this. So the ideal common mode gain should be equal to 0 and the ideal differential gain should be equal to infinity, right? So with this, if I list out the ideal features of an op amp, the features of an ideal op amp, one is generally, or we just mentioned before, Zn should be, input impedance should be infinity. Now the second thing is output impedance should be equal to 0. Then the third one is differential gain should be equal to infinity. Fourth one is common mode gain should be equal to 0. And if you have differential gain and common mode gain, there is another performance metric, like a figure of merit, what we call it as common mode rejection ratio, and that is written as AD divided by ACM. So common mode rejection ratio is nothing but the ratio of differential gain to common mode gain. Can you tell me what should be the ideal value of common mode rejection ratio? Can I get your response in the chat? Yeah, it should be very high, or rather it should be infinity. And finally, as someone put the message in the chat, bandwidth, it should respond for all frequency. That is what the need is, and we are looking for infinite bandwidth, even though in practical case none of these things will follow. Like you'll have a high gain, high input impedance, but it will never be infinity, right? But in the case of MOSFET based input differential pair amplifier, we can still say that the input impedance is very, very high. Alright, so these are the features of an ideal op amp. Now with this discussion, what I want to present now is, let us, even though we have drawn the op amp as this block, now with these features, let us little improve on this. So what we know is we have two input terminals. No, op amp has two input terminals. So one is V1, another one is V2. This is V out, and one we mark as minus and another we mark as plus, identifying one as inverting and one as non-inverting terminal. Then if you look at the first feature, input impedance is infinity. The meaning is these are the input terminals, and ideally if I draw, there should be a resistance like this, but in our case, since the input impedance is infinity, the resistance should remain open, right? So this is the case. Now the output impedance should be equal to 0. That means there should not be any impedance at the output. So ideally when I mark it, so if I have V1 and V2 terminals here, and if the output should be gain times of this, what I should ideally have here is a voltage source of this side. Let me just redraw this. Give me 1 second. This is V1, this is V2, this is minus, this is plus. Now so what I am expecting out of this op amp here at the V out is A times the difference input, so that I can get ideally from voltage controlled voltage source, which should have in this way. So what is this? This is A times of V2 minus V1, right? So when I am providing V1 and V2, what I am expecting is A times of V1 minus V2 in this form. But if in the ideal case, even this should remain as 0. There should not be any output impedance, so this should remain as 0. So this is the case. This is how we can show the internal diagram of an ideal op amp. So input impedance is infinity, output impedance is 0, and the differential gain is A times V2 minus V1, and you'll have the plus and minus terminal. So this is plus VCC and this is minus VEE. Alright, I hope you are following. Can I get some response in the chat? Alright, yeah, just look at this now. If I write V out as A times V2 minus V1, which is what I am expecting out of op amp, and where this A is called as the differential gain or the open loop gain of the op amp, right? Now If I write like this, I can also write that V out by this A is equal to V2 minus V1, right? When the output is A times V2 minus V1, I can also, alright, I think there is a question, Y minus VEE, alright. So I am just using the typical 7 4 op amps diagram here. So if your question is why not this is working with say plus VCC and 0, if that is your question, the answer is at least the op amps what we have, what we are using in the labs, the previous discrete op amp which is particularly based on BJT, there it works on dual power supply. We call it as dual power supply, which is having plus VCC and minus VEE. The difference there is, say for example, if your supply voltage is 12, you will have plus 12 as the maximum, the positive side, and minus 12 as the other side, and your signal will be always swinging around 0. Right, signal will be swinging around 0. If whether your input or output, whatever it is, it will be swinging around 0, and it can go up to minus 12. So the range is from plus 12 to minus 12. But these days you will see that op amps work on 1.8 or 1 volt supply, and there we will not see this kind of differential version, in the sense you will not see this kind of dual power supply version. Alright, okay. So where you will see is with respect to say 1 volt and 0 volt. Between the negative reference will be always 0. Oh, your question is why I put a negative sign along with VEE, is that your question? Oh, okay. Maybe I didn't get the exact question what it is. The other time, one more thing what I can give is, okay, yeah, fine. So this VCC and VEE generally, say for example, if you have a transistor here, the power supply, when we connect to this collector, we call it as VCC, and this notation is called as double subscript notation, that is usually given for power supply. Similarly, the other side what we have is emitter, that is why we generally use this notation of minus VEE. Alright, yeah. Yeah, so coming back to this, what we were talking here is V out by A can be written as V2 minus V1. Now, the moment you say A is infinity, what is the implication of that? When your A is infinity, this term is actually reducing to 0, or I can say that V2 minus V1 is equal to 0, right? That implies that V2 will be equal to V1, right? So this is one of the important property of an op amp. So since the differential gain is very high for an ideal op amp, when the differential gain is very high, we can see that both the input terminals will be at the same potential, and this property we call it as virtual ground property. It is not virtual ground property in this case, we call it as virtual short. What is the meaning of this? V2 and V1 are not shorted exactly. If you look at this, the V2 and V1 are actually in between, the resistance is very high. But from this relation, whenever we use an ideal op amp, when the gain is too high or when the gain is infinity, what happens to the input terminal, the difference between the input terminals will actually go to 0. And in that case, we can always say that V2 will be equal to V1. And this property is called as virtual short property, which is a very useful property when we use this op amp for many discrete applications. We will see shortly how this virtual short property is helpful. Now, when I say virtually short, this is not actually short. Physically it is not short, virtually it is short, and if V2 is at 0, V1 also will be at 0, because when the gain is too high, this relation holds good, right? Alright, so we'll also quickly see one thing which is, we'll come back to this virtual short property again. Now, from this discussion, you can just keep this in mind that when the differential gain is very high, you can see that both the input terminals will be at the same potential. Now, let me also quickly discuss about differential and common mode signals. So As the name suggests, when you say differential signal, it is a difference between two signals. It is the difference between two input signals in this case. So most of the time we represent it as Vd. Since it's input, we mark it as Vid, and that is equal to V2 minus V1. This is how we generally represent. Now, the moment you say common mode signal, it is the average of two input signals. It is the average of two input signals. So how will I represent that? Differential is marked as Vd. Common mode I will mark as Vcm. Since it is an input, I will mark it as Vicm. And if I want to represent the common mode version of the two voltages V1 and V2, I can mark it as V1 plus V2 divided by 2. Right. So if I can represent Vi, differential signal, and common mode signal, if there are two signals present as V2 and V1. Now if I want to write V1, how can I write V1 and how can I write V2 in terms of Vicm and Vid? Can I just get your response in the chat? So what I did here is, I have two voltages V1 and V2. I represented a differential voltage as the difference of that and the common mode voltage as the average of that. Now if I want to represent V1 and V2 each in terms of this differential and common mode signal, how will I represent? Any response? You have two equations. Now I want to write what is V1 and V2 in terms of Vid and Vicm. Alright, any response? Yes, V2 is Vid by 2 plus Cm, correct. So V1 is, you have the common mode signal which is Vicm. In both places you have that. Now V2, I mark it as Vid by 2, the plus Vid by 2, and the other one it is minus Vid by 2, right. So what is the implication of this? So what is the meaning of this? You have two signals V1 and V2 like this. Now when you do V2 minus V1, what I have is a differential voltage which is just Vid, and that time there is no common mode signal, or the common mode signal will actually go to 0. Alright. Yeah. So now if I represent this, V1 and V2 can be represented as, there is a common DC potential. I will mark this as Vicm. On that Vicm, the differential signal Vid by 2 is minus, so it will go in this direction, and the other one will go in this direction, right. So this is Vicm minus Vid by 2, and this is Vicm plus Vid by 2. This is how we represent two voltages in terms of its common mode and differential mode components. Is this clear? Any questions here? Alright, so we'll just wind up with a very small example where we will look at the internal structure of an op-amp. Say if you have questions, you can just post it in the chat. I'll be responding to that. So there is V1 voltage here. Say there is V2 voltage here. Now you have a voltage controlled current source which can be marked as a GM1 into V1 out of this. Similarly, you have another current source here, which is marked as GM into V2. Now these two are tied together and we have, say, a resistance R over here, right. So we have V1 and V2, and now say the differential voltage is available here as VID. Now what is the relationship between this VID and this V1 V2? When you are providing V1 and V2 here, I am getting VID here. I am just asking how to represent VID in terms of V1 V2. It is basically through this. You have two current sources here, right? One is GM-V1, another one is GM-V2. So I can represent the difference as GM-V2 minus GM-V1 into R. That will be the current, that will be the voltage VID here. Now again, if I have another, say, a voltage source here, a voltage source, say plus minus, and if I am calling this as GVID, this as the final V0. So what I want you guys to find is, assuming that this is internally right, consider this as one terminal and this as another terminal, this as output terminal 3. Given that the value of GM is say 10 milliamps per volt, so basically GM is transconductance. Given that the value of resistance is 10 kilo ohm, and also given that the value of G, the gain factor, there is equal to 100. So what you can find is, you can find what is the overall gain of the structure from input to output, or the relationship between V0 and, or if I represent V0 as A times V2 minus V1, what is this A factor? That is a question. So I hope you understood what I have drawn here. I have drawn certain current sources and voltage sources, and then I have put inside an op-amp. Now what I am asking is, what is the relationship between Vout and input V1 V2? Yes, that is correct, Sanket. So when you look at VID, or VID is a voltage across the resistance R. What is this voltage? The voltage here is the current flowing in this terminal into current flowing at this node into the resistance R. What is the current flowing here? You can see that this current is here and this current is flowing in this direction. So how will I represent VID? So if I write VID, I can write VID as GM times V2 minus V1 into R. This is your VID, right? So how can I write VID? GM, if it is given as 10 milliamps into V2 minus V1 into R is 10 kilo ohms. So I can write that VID is equal to 100 times V2 minus V1. That is what I can write here, right? VID is 100 times V2 minus V1, and now if I write what is Vout, so looking at Vout is equal to G times VID. Given that G is 100, so 100 into V0, G times VID. So VID is what? 100 times V2 minus V1. So I can write V0 divided by V2 minus V1, which is the overall gain of the structure, as 10 to the power of 4. So V0 divided by V2 minus V1 is basically A, and that A is equal to 10 to the power of 4. So how much is 10 to the power of 4? 10 to the power of 3 is 60 dB, so I think this is around 80 dB. 80 dB is the open loop gain, and this is what we usually check, or this is what we usually need for a op-amp. Very high gain is what we are expecting from an op-amp. Alright, so I think this today we will wind up here. We will continue from the next. The remaining will be like how we will go about will be from the applications part.